Okay, welcome back. And so today we're going to talk about how to run a factorial ANOVA in R, which is when we have more than one categorical predictor. And so this time we're going to be talking about, does word recall vary by task complexity and age? So in the previous video we looked at whether or not someone's ability to remember words varied as a function of the complexity of the brain teaser they engaged in beforehand, for lack of a better word. And we found that basically as your task complexity increased, right, your ability to remember words later also increased. And we talked about the specific interpretation of those results in the previous video. Again, that was the one-way ANOVA. And this time we are now going to add in age as well. So we're looking at whether or not word recall varies both as a function of the type of brain teaser you do beforehand and your age. And as usual, the first portion of the video we'll talk about code, and the second portion of the video we'll talk about how to interpret and report the results. And I will explain what these box plots are showing in just a minute. But for now, let's go ahead and get started with the code. Okay, and just as a recap, as always, you can find the code and the data set on my GitHub page, and the link is in the description. And again, as I mentioned in the one-way ANOVA video, don't let the word GitHub intimidate you if you're not familiar with it. You literally just click the link I have provided, and you can download and view the data that I have and the code. So just because it's called a GitHub page, it's not some fancy magical thing. I always thought it was when I first heard about GitHub, but it's really pretty simple. You can literally just click the link and get access to my code. So anyways, we're going to look at the two-way factorial ANOVA, and we're going to look at a situation where we have equal sample sizes, which is also called a balanced design. And what I mean by that is if we visualize our different groups where we have 5 different conditions and 2 different age groups, young and old, well, we have 10 possible groups, right? We can have young condition 1, young condition 2, young condition 3, so on and so forth, and then old condition 1, old condition 2, so on and so forth. And so the equal sample sizes is a situation where we have the same number of participants in each of those groups. And the ANOVA gets a little bit more complex when you have unequal sample sizes. So for now, we'll stick with equal sample sizes, and then in the next video, we'll go over a result for how to do unequal sample sizes. We might actually squeeze that into this video as well. Yeah, I think we'll squeeze it into this video as well, but we'll start with an example where we have equal sample sizes, and then we'll proceed to unequal sample sizes. So yeah, we'll cover that in this video. But to start with, again, we'll start by looking at a box plot of the main effects, and what I mean by that is if I run this code, I will explain to you what's going on. Okay, so what we have here is this is the overall box plot or the distribution of word recall scores. So this is the number of words all participants were able to recall, and this is the distribution where we don't consider group, whether it's condition or age. We just look at the distribution of all participants' word recall scores. And then over here we have the main effects or the marginal distribution of recall by just age. So the distribution of the number of words recalled for the old folks and the young folks. Right away we can tell it looks like there's a pretty significant difference. And you might be wondering why the older folks are able to recall more words than the younger folks. You might think it would be the other way around, but as we'll see, there's a reason for that. And then we also have what we talked about in our previous one-way ANOVA video. We have our box plot for the recall scores by task condition, where the 1 through 5 scale is basically the level of complexity of the task they did beforehand. So whether or not they just, for example, read the words, whether or not they maybe did some type of memory exercise, and so on and so forth, right? It's increasing in cognitive complexity. So basically we see that if we ignore age and we just look at this relationship between task complexity and the number of words recalled, there does appear to be a relationship. And we saw in our one-way ANOVA that that is the case. So this is just a good way to visualize from the start what's going on. And I won't go into the detail of what we've got going on here, but basically you just sub out your outcome measure and one of your categorical predictors, and then you say what that is and what your outcome measure was, and then this is the title of your plot. That's for the first box plot, and then this is where you would say your overall outcome measure, and we're not specifying any type of categorical variable here. We're just looking at the distribution of recall in general. And then this third plot was the one where we looked at the distribution of recall scores for our other categorical predictors. So the first one for us was age, then we had everything ignoring age and condition, and then this one is just condition. And so again, you could do this with your data and just sub out your predictors where necessary. And then another visualization we can do is we can look at some side-by-side box plots. And so what we see here is that on the bottom, the x-axis, we have our condition level, but then we have allowed for two different box plots, side-by-side box plots for the age groups. And so the turquoise is the old participants, and the coral or the pink is the young participants. And again, we've allowed this to now vary, for across both variables basically. And so as we see, it does look like this general trend seems to be present of task complexity, increasing with recall increasing with task complexity. But if we look, it seems like there might be a different type of trend for the older participants relative to the younger, because we can see the younger participants, it kind of levels off once we get to level 3, whereas it steadily increases for the older participants. And that's what our ANOVA is going to look at. And so you would just specify ggplot, the name of your data frame. This is whatever you want, whichever categorical predictor you want on the x-axis. This is your outcome measure. And then you'll specify the color, and the fill will be your other your other categorical predictor. So again, it's up to you whether or not you want to have, which one you want to have on the x-axis and which one you want to break up, to do the side-by-side colors. We can also look at another version of the exact same thing, but just flip which variable's on the x-axis and which one serves as our coloring variable. And so what we see here now is on the x-axis we just have the young participants and the old participants, and then we've allowed the side-by-side box plots, the color, to represent the condition. So these both visualize the same thing. It's up to you which you think is more appropriate and which you think is a more powerful representation. I like this one a little bit better because it shows us really clearly how this trend differs for the young folks and the old folks, or how it looks like it's going to differ. And then the next thing we can do is we can look at what's called a interaction plot. And so here we're going to specify our first categorical variable, we're going to specify our second categorical variable, and then we're going to specify our outcome measure. And then we're going to say that we want to look at the means. So we want to look at the mean outcome level or mean word recall for our different levels of our categorical predictors. So we'll run this code. And then what we have here is this is just a line plot of kind of what we saw with the box plots with that same trend. And so the dashed line, that kind of hard to say, this is kind of a crappy plot, but the dashed line, that represents the young participants, and then the solid line represents the old participants. And we can see kind of what we already saw with the box plots. So now we can get our descriptive statistics. And so basically what you would do is you would just sub out your outcome measure here, and then both of your categorical predictors, which for us are condition and age. And then this first line is giving us the mean recall by condition and age. The second line is giving us the variance by recall and age. And then these other lines of code are just formatting it so we can get this all into one table, and then we're rounding our digits. Again, none of this is strictly necessary, right? You don't have to do it this fancy way. And so we'll run our code, and then we'll come down here, and we would just want to print the results, right? So all we do is we'll specify the name of what we just created. And so we made this AOV2 underscore means and variance. And again, where I got that from is right here. In this line of code, I joined the descriptive statistics for the mean by condition and age, and then the descriptive statistics for the variance by condition and age. Then I joined them together to make this AOV2 object, and that's what I'm printing right here. And so what we're looking at is a column where we have the condition level, the age group, and then the mean recall, number of words recalled for each cell, right? And when I say cell, I mean each specific combination of our two variables. So this first cell is condition 1 and young. Second one is condition 2 in young, and then so on and so forth, right? And so we see the mean recall and the variance. Okay, and then we can also run this line of code right here to get a slightly prettier version, and all it really did is it just added some lines to make it easier to read. We also might want to take a look at the marginal means. So basically ignoring condition, what are the mean levels of recall for our different age groups? So I'm going to create this object called age marg. I'm going to say recall predicted from just age, and then I want the mean. And here is the marginal mean for young and old, right? So the old folks have a marginal mean recall, number of words recalled, that's higher than the young folks. And we can do the same thing for condition now. And here we see kind of what we saw in our one-way ANOVA, that if we ignore age, we see these different marginal means, marginal recall levels. And then we might want to just get the overall mean, or the grand mean, right? So ignoring our conditions, what's just the overall average number of words recalled? Okay, now let's get to the good stuff. So we're going to fit our two-way ANOVA with an interaction term, okay? Now, when I say interaction term, all that means is that I am also accounting for the fact that in addition to there being some main effect of age and some main effect of condition, there also is an interaction. And I'll explain that in the PowerPoint more, but basically what we're looking at is the main effect, sorry, this isn't the one I wanted. Let me go back. Yeah. So the main effect, right, would be just the marginal differences between our condition and our age, right? So the marginal difference of old versus young, and then the marginal differences of the word recall by condition level, okay? So those would represent the main effects, right? We're looking at the effects of a categorical predictor, ignoring the other one, okay? The interaction is when we then consider the fact that this trend might differ, or both of these trends might differ based on the other one. So in other words, right, we saw the main effect of condition in the one-way ANOVA was significant, right? As condition increased, we had this kind of like overall trend that task complexity would, as task complexity increased, we saw this overall trend that word recall would increase as well, right? But the interaction is going to say that the specific effects of condition upon recall vary based on what age group you're in, right? And we can see that in our plots here, right? These lines aren't parallel, okay? And then another way of phrasing this would be, does the effect of age, so the differences between the young and old participants, does that vary based on which condition they were in? And the way we would represent that visually would be this plot right here, right? So again, we would say basically, okay, well, let's look at the side-by-side comparisons for the young and the old, but we're going to do that for each level of condition. And what the theory would be that instead of just worrying about the overall differences between young and old, we're going to look at specific levels of our other variables. So that's what the interaction means. It's this idea that you're looking at the possibility that the effects of one of your predictors are going to vary based on the level of the other one. And so that's what I mean when I'm saying that we are allowing an interaction term. So the way we're going to do this is we're going to make our ANOVA model, or our object. So we're going to call it AOV2. We're going to do our outcome, recall, tilde, predicted from, or as a function of, condition, and then we're going to add this star, condition star age, or asterisk age. And what this does is this is equivalent to saying recall predicted from condition plus age plus the interaction of condition and age. So that's basically what this star does. It's a shortcut to write this right here. So again, the star just means that you are going to allow for an interaction term. We specify what data our data set came from. Now I need you to take a leap of faith with me right here. This contrasts thing is not specifically necessary for when you have equal sample sizes, but it will be necessary when we have unequal sample sizes, and it's not going to hurt anything to do this now. So I need you to just take a leap of faith with me and go ahead and do this, right? And so I know it looks complicated, but all you're doing is you're just adding this little line where we're saying our contrasts are going to be, and then we have a list of what they are. And so we just specify whatever your first predictor is, your categorical predictor, which for us is condition, equals, and then we're going to ask it to use the contrast sum contrasts. And then we're going to do the same thing for age. We just say age equals contrast sum. This is because by default, R will use dummy coding or treatment coding for the categorical predictors, where everything is compared to the reference group, right? Whereas this will change that. And again, it's not strictly necessary for when you have equal sample sizes, but it's not going to hurt anything. So I recommend that you do it because you'll need to do it when we start dealing with unequal sample sizes. Also, it will affect the sums of squares when we use type 3 sums of squares. So again, don't worry about that now. Just go ahead and do this. It's not going to hurt anything. But it's going to save you a step later when we look at unequal sample sizes. So it's not complicated. You just add this line that says contrast equal list, and then you specify your two predictors, and then you just say that both of them are going to be contrast sum contrasts. So we'll go ahead and fit our model, and then we'll come down here, and then you also have to do this line of code. And again, this is the same thing, not strictly necessary when you have equal sample sizes, but it's not going to hurt anything. So I would just say go ahead and do it now. And so we're going to specify fit2, our new fitted object is going to be Anova, and then whatever you called your object above, put that down here, and then type is type equals 3 for type 3 sums of squares. And again, there's no difference in the sums of squares when you have a balanced design, but just, take a leap of faith with me and do it anyways. And so now we'll take a look at what that summary gives us. Okay, and I'll go over this in the PowerPoint, but basically same thing as with the one-way ANOVA. Ignore the intercept here, just ignore it. And then we see condition. This is the main effect of condition. This is the main effect of age. This is the interaction down here between condition and age. And so it looks like we have significant main effects, significant main effect of condition and age, and the interaction between condition and age. Now we'll talk about it in a few minutes. Some people say that if you have a significant interaction, you should never interpret your main effects. I don't agree with that. There's certain situations where you can still interpret your main effects, but we'll talk about that when we go to the PowerPoint. Important thing to note is that we do have significant main effects and interaction effects. Okay, and so we can get a slightly fancier version of what we're looking at right now. Just add some lines, make it a little pleasanter to look at. And then if we want to get our effect sizes, again, that's going to be the eta squared. We can do eta squared and then fit2, which again was whatever you called this up here. And then we want the full eta squared. We don't want partial eta squared. If you wanted partial, you would say partial equals true. So we'll go ahead and run this. And here's our point estimates and our confidence intervals. And we'll go over how to interpret that in the PowerPoint. But right away we can see that condition does appear to have a larger eta squared relative to age and then the interaction. But again, it gets kind of complicated when you have the interaction terms. We'll go over that in a minute. All right, now, so let's just recap what we've established. We've established that, We've established that our main effects of age are significant and our main effects of condition are significant. And we've established that there is a significant interaction between age and condition, right? So basically, what we have to decide now is we need to look at exactly what that interaction looks like. So in other words, we know that the effect of condition varies based on what age group you're in, or vice versa. We know that the effect of age varies depending on what type of task condition you're exposed to. We're going to look at what's called the simple main effect to specify exactly, okay, well, if we look at just one level of our predictor, what is the effect of the other predictor. So in other words, if we look at just the young participants, what is the effective condition? And then we're going to compare that to saying, okay, if we look at just the old participants, now what's the effective condition? And so this is kind of like a way of teasing out exactly what's going on with your interaction, because all the significant interaction tells us is that there is some interaction, right? The main effect of condition does depend to some degree upon age and vice versa, but it doesn't tell us, that model summary doesn't tell us exactly what that relationship is. Our box plots give us a good idea, but we need to test the simple main effects to see exactly what's going on. And again, all a simple main effect is, it's saying, okay, let's zero in on just one level at a time for one of your categorical predictors, and then see what the effect of the other one is for just the folks that are in this one level of the other one, and then the other level of the other one. So again, the simple main effect of condition for just the young participants, and the simple main effect of condition for just the old participants. And again, you can flip it based on what you think is most relevant to your research. So if I wanted to instead say the simple main effect of age at the various condition levels, I could do that as well. But I think it makes more sense to say, okay, no, let's just look at just the young folks and then just the older folks and see what the simple main effect of condition is. And so the way we do this is we're going to subset our data by the group level that we are trying to isolate. So in other words, if I want to look at the simple main effect of condition for just the old and just the young folks, then I need to subset so that I have just the old folks and then just the young folks. So you make a new data set, for lack of a better words, a little data subset. I'm going to call it age.o for age is old, and then the subset of my data set, and then the variable, the age rate variable, equals old. So this is saying to subset only those participants whose age status matches the old group, right? And then we're going to do the same thing for the young group. So we'll go ahead and run this. And so now that we've isolated this, now we can go ahead and run a one-way ANOVA for the effective condition for just the old folks and just the young folks. And so we're going to call the first one the simple main effect of condition for the old folks. And we're going to do AOV, recall our outcome measure, tilde as a function of or predicted from condition, and then the data now is going to be just the older subset, and then we'll do the same thing for just the younger subset. So we'll go ahead and fit both of these ANOVA objects, right? And so whatever level you're trying to isolate, that's what you'll sub in for age, right? So if, for example, you're interested in the effect of maybe what department a professor works at by gender, what you could do is you could take a subset of just the female professors and just the male professors, and then run a one-way ANOVA to say, okay, what's the effect of which department they work on for just the just the women professors and just the men professors, right? And so that's an example of when you could do the same thing with different predictors. So again, it's just depends on what it is you're trying to look at. Now we're going to come down here, we're going to look at our results. And so what we need to do is we need to make a fitted object. So I'm going to call it fit, simple main effect, old, and then ANOVA, and then whatever you called that object above, we called it SME condition old above. And then I'm going to specify type equals 3. And again, not strictly necessary when you have equal sample sizes, but it's not going to hurt anything. So I recommend just going ahead and doing it. So we'll do that. And now we can get a summary of the effective condition for just the older folks, right? And again, ignore the intercept as always. And so we look and we see that condition is significant for just the old folks, and our F value is 53.06. We can also get the eta squared, which I think is probably going to be more useful in this case, again, for just the fit SME old, the simple main effect for condition for just the old folks, and then our partial equals false because we want full eta squared, not partial eta squared. And so here's the eta squared estimate of condition for just the older folks. So for the older folks, condition explains about 83% of the variation in word recall. Now we're going to come down here and do the same thing for the young group and compare them. So fit, simple main effect young equals ANOVA, and then the simple main effect object we made above for just the young folks, and then type equals 3. We'll print it, look at our results, and our F value here for condition is only 9.08. And then more importantly, right, if we look at a squared for just the young folks, it's 0.45. So 0.45 or 45% of the variation in recall for the younger folks is explained by condition, right? So another way of saying that is for the younger folks, 45% of the variation in word recall is explained by condition. Whereas for the older folks, 83% of the variation in word recall was explained by condition. And if we look at our box plot, that kind of makes sense, right? What we're saying is that for the older folks, condition does explain more of the variation in word recall, and that matches up with what we see with this trend being, more noticeable for the older folks than the younger folks. You can also get estimated group means, and so what you're going to do is you're going to create an object, so I'm calling it EFF, you can call it whatever you want, then you say effect, and then the term, we want to look at the condition by age. So for whatever your two predictors are, it'll just be predictor 1, star, predictor 2, and mod. For us, it's AOV2. It's going to be whatever you saved your initial ANOVA object as. That's what you're going to specify. So we'll go ahead and run this. Oh. Okay, I got an error. I had to come back up here. This should be effects. Previously, I had this as effect, but it should be effects. If you get the code from my GitHub, that should be accurate. But if you're just going based off of what you see on the screen, you need to load effects with an S instead of effect. Okay, so now we'll come back down to what I was trying to do. Sorry. Jeez. Okay, so again, we're going to come back here. We're going to say EFF, whatever you want to call it, and then effect, and then specify the term, which is going to be predictor 1, star, predictor 2, and then the mod, whatever you save the mod as. And then now we'll print it. And so this gives us the estimated means, or estimated group means, right? So for the young folks in condition 1, the old folks in condition 1, so on and so forth. We can also do summary of this object that we created, and it gives us a confidence interval. So we have the lower 95% confidence limits for that estimated mean outcome measure for each group, and then the upper 95% confidence limits. We can also look at post hoc pairwise tests if desired. Now, a word to the wise, this can quickly get complex, right? So let's take a look at it. And again, what I'm going to do first is I'm actually going to look at it just for the simple, just for the subset, like for the simple main effect of condition for just the old folks and just the young folks. So basically what I'm going to do is I'm going to look at the specific differences in recall by condition level for just the old folks and just the young folks, instead of like looking at it all lumped together. So it'll make more sense when I run the code. And so what we see is this is going to give us the pairwise comparisons of all the different condition levels. So in other words, if we look at our box plot, right, we just saw that for the older folks, right, the simple main effect of condition on word recall is stronger for them, but we don't know like any specific differences between condition 1 versus condition 2, 2 versus 3, 2 versus 4, so on and so forth. So just like we did with the one-way ANOVA, we can do pairwise tests to test the specific comparisons within each level. So for just the older folks, which conditions are associated with different, mean outcome scores, and then just the younger folks, right? And we can compare that and see, okay, well, maybe for the older folks, group 5 had a significant difference from group 4, or condition 5 had a significant difference from condition 4, but then for the younger folks, maybe 5 and 4 didn't have a significant difference, right? And so that's basically what we can do with these post hoc tests. And so we can do this for just the old folks and then just the young folks. And I'll go over how to interpret this and write this up in the PowerPoint. But the way you read this is basically, this shows us each comparison. So this is for the younger folks, this is group condition 2 versus condition 1, and then we can see that there's a non-significant difference. We do have a significant difference for 3 versus 1 and 4 versus 1 and 5 versus 1, okay? And then down here at the bottom, right, for the younger folks again, when we look at group 5 versus group 4, not a significant difference. 5 versus 3, not a significant. 4 versus 3, not as significant. And if we go back to our box plot, this makes sense, right? Because this is group 3, or condition 3, condition 4, condition 5 for just the young folks, and it doesn't look like there's any types of differences. Okay, and I'll show you how to write that up. And we do the same thing for the other level of our subset, which was the older folks as well. And then now we can also look at model assumptions and diagnostics. So the first thing I want to do is I want to take a look at the variances by condition to test whether or not not to test, but rather to evaluate whether or not I do have consistent variation within groups. And if we look at this box plot again, the spread does look like it differs, fairly significantly between our different cells, where a cell just represents a combination of young and condition 1 or young and condition 2, right? Each of these box plots represents a cell, and we're looking at the spread or the variation across these different cells or groups, and it looks like there does not appear to be a consistent spread, right? There's quite a bit of variation. But we can take a look at that, and the code I just ran is just saying, okay, I want you to this, but the code I just ran is saying, okay, aggregate your outcome measure as a function of predictor 1 and predictor 2, and then get the variance, right? And then this line of code is just naming that column variance, so we know where we're looking at, and then this is just giving us a fancier variance table. Okay, and so again, what we see here's the variances for each of our cells, right? Our groups. So condition 1 and young, variance of 3.3. and then so on and so forth. And so we can see right away that if we use the threshold that we talked about in our one-way ANOVA, where we're going to compare our largest to our smallest to see whether or not what that ratio is, whether or not we think our assumptions of constant variance are violated. Our largest here is 20.26. Our smallest is 2.05. The ratio of that of 20 divided by 2 is a ratio of 10. And our threshold is typically 4 to 5, so it does look like we have heterogeneity of variance. But for the purposes of this example, we'll just proceed like we don't. And again, there is debate about the degree to which heterogeneity of variance really affects things. If you have equal sample sizes, the ANOVA will be more robust or less impacted by heterogeneity of variance or unequal variance. But if you have unequal sample sizes where you have different numbers of people in each combination of like age and condition, for example, then heterogeneity of variance is a lot more important. But there is some debate about just how important homogeneity of variance is, and generally it's accepted that the ANOVA is relatively robust to having unequal error variances, but it's still something you want to check. Okay, we can come down here and get our plots. And so you just type in the plot AOV2, which is the name of the ANOVA model that we saved earlier. I think I have an error in my code somewhere. Oh, I had a typo from before, sorry. Okay, I'm just going to run that. And here we go. So that's one of them. I'll go over them in the PowerPoint. And here's the other three. And again, I'll go over them in the PowerPoint, but you can zoom in and get a bigger version of them. We're going to also extract our residuals. So we're going to make an object called resid2. You can call it whatever you want. And then residuals and the name of your ANOVA object that we created. And then we can look at a histogram of our residuals, and we see that they do appear to be relatively distributed normally around a mean of 0. Okay, and we'll go over again interpretation in the PowerPoint. So we can also run this as a regression model. And so the first thing I'm going to do, you don't have to do this in real life, I'm just doing this for illustration purposes, is I'm going to make a new version of condition that treats it as a numeric variable, and a new version of age that treats it as a numeric variable. And then I'm going to save a regression model, but it's the same regression model that we made our ANOVA model, right? It's just recall predicted from condition star age. So there's an interaction of condition and age. Then we can get a summary of our results. Whoops. There we go. Sorry about that. And so what we see is that in this instance, the interaction term is significant. I know we got non-significant results for the main effects of condition and age, but it's a little bit different, when we're treating these as numeric variables and running a regression model instead. The important thing, though, again, is that we have this interaction here. So yeah, I don't want to get into all that. I just wanted to illustrate that you can also run an ANOVA as a regression model, and it's absolutely equivalent, right? We still get the result that, yeah, the degree to which, condition affects someone's recall varies based on their age and vice versa. And then we can also, we can also get the semi-partial squared, and that's going to be equivalent to the eta squared that we looked at earlier. So we could just do eta squared m2 partial equals false. And then we have our eta squared as well. So I'm going to save that real quick before I lose it. Okay, so now we're going to come back to our PowerPoint and talk about the results. And so we're going to make a table just like we did with the one-way ANOVA. This is the easiest way to display your information. And all this is the stuff that we got from our ANOVA model summary from before and our effect sizes, our eta squared. And so what you would do is you just put your first predictor, your second predictor, and then the interaction term, and then the residuals. And so then you put in your degrees of freedom, the sums of squares, the mean square error, and again, this is all in the output that we get from running our code, the F value for each of them, and then the P value, the significance test, and then the estimate of the eta squared. And again, just pull this all from the code, and then it's also really helpful to include a plot as well. And so now we'll get into how we actually interpret the results, but this is how I would display them in a table. And so let me go back real quick. And so like we talked about, we saw that there was a significant main effect for condition and for age, but we're more interested in the interaction term. And this is typically the case, right? When you have a significant interaction, that's almost always what you're really interested in, right? Because we're not so much interested that condition overall has an effect and that age overall has an effect. We're more interested in the fact that the task condition seems to have a different impact depending on what age group folks fall into. And specifically, as we saw from our plot here, for the older folks, it looks like that that association seems to be stronger, right? Okay, and so this is how we would display the results of these simple main effects tests that we looked earlier. And so we're just going to make another table, but now it's basically just a one-way ANOVA of recall by condition for the young group and recall by condition for the old group. So this is just the output of the simple main effects models that we looked at in R, where again we're looking at the effective condition upon the number of words recalled for the young folks and for the old folks. And like we said before, we see that our F value is larger for the older group and the eta squared is much larger for the older group, right? And so this is a really powerful interpretation, or a really powerful visualization, right? For the interpretation of this is that for the participants in the older group, or the older participants rather, the task condition or the complexity of like the brain teaser they engaged in explained 83% of the variation in the number of words they recalled, whereas for the younger participants, the condition effect only explained 45% of the variation in word recall. So it was significant for both level. Condition had a significant effect for both levels of our age group, but the exact magnitude differed. So this is one of those examples where we can also interpret the main affected condition because it is present for both the younger folks and the older folks. But there's going to be many instances in which it might be significant for one level but not the other. So in other words, there might be a situation where the overall affected condition might be significant, but then once we look at our results and we see we have a significant interaction, well, we might probe our interaction and then see that it could be the case that for the younger folks specifically, maybe condition doesn't have an effect, or for the older folks specifically, maybe condition doesn't have a significant effect, right? And so this is an instance where condition does have an effect for both levels of our age factor, right? But there could easily be instances where that's not the case. And if that's not the case, that's a situation where it might not make sense to talk about main effects, right? Because if we have a significant main effect for condition, but then when we break it down and see that that's not present for one group, but it is present for the other age group, then it's no longer necessarily appropriate to talk about the significant effect of condition, because in that instance we would know that it doesn't apply to both groups, right? It only has a significant effect for the older participants. And to be clear, that is not the case in this example. I'm just giving you a situation in which the main effects might not make much sense to talk about based on the results you get when you probe your interaction. In this specific instance, we do see that condition has a significant effect for both levels of our age group, or both age groups rather. So we can talk about the main effect of condition, but we note that the magnitude of the effective condition, the degree to which condition explains the number of words recalled, that does change based on the age of the participant. And so this is how we would basically plot the individual group means, kind of like we do with the one-way ANOVA, but now we just have two different groups. And so the way we interpret this is, if you see this note at the bottom, it says within each row, means sharing a superscript do not differ significantly at the home-adjusted 0.05 level. So what this is saying is, if we just go along this row, so just for the old folks, or the younger folks first, okay, the mean recall, which is what's shown here, so the number of words recalled for the young folks in task condition 1 was 7, for example. What this is showing us is that the mean recall for the young folks differed significantly for the folks in 1 and 2 relative to 3, 4, and 5, but for the younger folks, those in 1 and 2 didn't differ significantly from one another because they have the A, they're sharing the A in their superscript. And for the younger folks, those in groups 3, 4, and 5, or conditions 3, 4, and 5, did not have significantly different recall scores from one another. And that's why they're sharing that B, because they don't differ significantly from one another. But again, 1 and 2 collectively all significantly differ from those younger folks exposed to condition 3, 4, and 5. And so that's why they have 1 and 2 for the young folks have A's, and 3, 4, and 5 have B's. Okay, whereas for the older folks, if we look at it, we see that for the older folks, those in task condition 1 and 2 don't differ significantly from one another, but they do differ significantly from 3, 4, and 5. But what's interesting and what's different about the older folks and the younger folks is that for the younger folks, right, 3, 4, and 5, there were no differences. Okay, so whether for the younger folks, whether someone was in condition 3, condition 4, or condition 5, that didn't significantly affect their recall, right? There wasn't a significant difference. But for the older folks, there are additional differences amongst 3, 4, and 5. So specifically, for the older folks, 3 and 4 don't differ significantly from one another because they both have a B. But 3 and 4 do differ significantly from those in group 5. 3 differs significantly from those in group 5 because 3 has a B and 5 has a C. And then 4, I misspoke a second ago, 4 does not differ significantly from 5 because it also has a C. So let me say that again. For the old folks, those in 1 and 2 differ significantly from those in 3, 4, and 5. Okay. But for the older folks, those in group 3 do differ significantly from those exposed to condition 5. Whereas that was not the case with the younger folks, right? For the younger folks, 3, 4, and 5 are indistinguishable in terms of their mean recall. But we do have some additional effects of condition for the older folks, right? So if you're in group 3, you have significantly lower average recall than if you're in group 5. And if we go back to our plot, that kind of makes sense, right? So again, this isn't the best plot, but the solid line is the older folks, right? And so we see that this trend continues upward as we go from 3 to 4 to 5, right? So 5 is significantly greater than 3 for the older folks, whereas for the younger folks, the dashed line, 3, 4, and 5 kind of level off. So it does make sense. Excuse me. Okay, so what can we say? Well, the positive trend of increased task complexity being associated with greater recall is present for both age groups. So in other words, the main effective condition is present for both age groups, but it's to a greater degree in the older participants. The trend seems to level off for the younger participants, but not the old. And then this indicates that maybe for the older participants, maybe cognitive exercises are especially important for memory. And this is just, me theorizing, right? But the reason you might think that is because for the older participants, right, as you engage in more and more complex like brain teasers or exercises, your recall continues to be affected by that. Whereas for the younger folks, right, it's maybe not as important, right? It kind of levels off. And then we could also say that the effect size of condition was noticeably greater for the older participants than for the younger participants. Quick note, this table is in APA format, so if that's something you care about, the table is in APA format. The bullet points are informally stated. I'll show you how you would write this formally right now. So this looks awful, and I'm not going to get too into depth. You can access this and copy and paste it, for if you care about APA format and formal write-ups, but I'll go through it very quickly. A 5x2 condition by age Factorial Anova was employed to investigate the effects of age group and task complexity upon recall. Each effective was tested with a mean square error of 8.0. I just got that from the tables we looked at. Significant effects were found for the main effective condition, the main effective age, and the interaction. The significant interaction was further investigated by testing the simple main effects of task condition for each age group level. For the younger participants, task condition had a significant effect upon recall, and then give all the information as well as the eta squared. And then we would say pairwise comparisons. Again, this is for the younger participants. Pairwise comparisons conducted using 2 key HSD tests indicated that for the younger participants, those who engaged in task conditions 1 and 2 recalled significantly fewer words than those in conditions 3, 4, and 5, and then all other comparisons for the younger participants fell short of significance. In contrast, for the older participants, task condition had a significant effect upon recall, and then state the results of that one-way ANOVA for just the older participants with the eta squared. For the older participants, those who engaged in task conditions 1 and 2 recalled significantly fewer words than those in conditions 3, 4, and 5, and those who engaged in condition 5 also recalled significantly more words than those in condition 3. And then lastly, we'll look at our regression diagnostics. And so what this is showing down here on the left is on the x-axis we have our fitted values or our predicted values, which is just the mean level of recall for each individual group or combination of condition and age. And we're looking to see, we want this red line to be horizontal where there's no pattern, and we also want the spread of these residuals to be constant, the vertical spread to be constant across our fitted levels. It appears that it's not great, but it's not awful either. And then if we look at a histogram of our residuals, we can see that they're distributed normally around 0. Not quite normally. It looks like we have some positive skew, but it's not awful. And then if we look at our QQ plot, same thing. It looks like as we increase in our residuals, right, we do have a degree of positive skew, but it's not awful. In this particular case, as we saw earlier, our assumptions about homogeneity of variance and the normality of the residuals, they may be questionable in this instance, right? But it's not the worst I've ever seen either. Okay, and so now I want to come back really quickly, and I want to talk about how we would run a two-way factorial ANOVA where we have unbalanced design or unequal sample sizes. And the situation we're going to look at is a different data set. Now we're going to look at legal violations as a function of what state someone lives in, whether it's North Carolina or Virginia, in their intoxication, whether they're drunk or not. So I'm going to load this data set here. I'm going to go ahead and view the data set. And so here we have state, either North Carolina or Virginia, and then condition, either drunk or not drunk, and then DV stands for drinking violations, right? Whether or not they had a violation. So the first thing we'll do, and I'm going to skim through this because of the way I structured the earlier Factorial Anova, where we had equal sample sizes, these steps are going to be pretty much the same for the unequal sample sizes. So I'm going to kind of go through this fast. I just want to show you what happens, right? So we'll go ahead and set our factor levels, just like we always do. But now when we run a cross tabulation of the frequencies, the number of participants in both of our predictor levels, right, so state and condition, when we do that, we see it's uneven. So if we look at North Carolina, the North Carolina participants have 4 who were sober, 10 who were drunk. But for Virginia, there's 11 who were sober and 5 who were drunk. This is a problem because now we have unequal or unbalanced design, and specifically our groups, right, are no longer orthogonal. And what I mean by that is that there is a correlation between what state you're in and whether you're sober or drunk. So because these aren't balanced, if I know that someone, a participant was from North Carolina, right away there's a greater chance that they're drunk. And if they are from Virginia, there's a greater chance that they are sober, right? So the reason this is important is because when we go and we try to partial out our variance and see, what proportion is due to state, what proportion is due to condition, and then we try to look at the interactions, right? There's going to be this lack of clarity, basically, because these aren't orthogonal, right? In other words, it's going to be hard for me to evaluate whether or not differences I see between North Carolina and Virginia are really due to a difference between North Carolina and Virginia, or due to the simple fact that North Carolina had more folks that were drunk and Virginia had more folks that were sober. So hopefully that makes sense. As before, we'll start by looking at a box plot to represent our main effects. And so what I want you to look at is that we see that North Carolina, it looks like they have a significantly higher number of violations than Virginia. But as we saw, North Carolina had a significantly, not a significant, but they had a lot more drunk people than Virginia did. So the question here is, if we were to just look at this box plot, it would look like North Carolina participants had more violations than Virginia participants. But we also come over here and then we look at drunk versus sober. Well, we see that obviously those who are drunk have more violations than those who are sober. And we saw from when we ran our crosstab that North Carolina had many more drunk participants and Virginia had many more sober participants. So the question is, and this is reflective of a paradox, right, a reversal paradox, the question is there really a difference between North Carolina and Virginia just due to state, or are the differences in violations instead due to this issue of where we have more drunk folks in the North Carolina sample? So that's the problem with unequal sample sizes. And then we can look at a plot where we actually do account for side-by-side comparisons now. And so now we look at the sober folks, and then the color represents the state. And sure enough, now it looks like there's not much difference between state, because if we look at just the sober folks only, well, North Carolina and Virginia have the same distribution of drinking violations in terms of like the median, right? And roughly the same, overall distribution. A little bit more spread in the Virginia. But anyways, you get the point. The point is that when we control for, sobriety status, right, we start to see that this difference in states may not be present after all. And we can look at the flip, where now we have state on the bottom, so North Carolina, Virginia, and then the colors represent sober and drunk. And so again, it looks like for both North Carolina and Virginians, obviously the drunk folks are going to have more violations than the sober folks. We can get an interaction plot to see if there's an interaction, and it doesn't look like there is. The solid line is kind of hard to tell. The solid line is the drunk folks, the dashed line is the sober folks. And what this shows us is that North Carolina and Virginia on the bottom, well, once we isolate out the the intoxication status, it doesn't look like there is a difference between North Carolina and Virginia, or state rather, right? There's a flat line, but there is obviously a big difference overall between drunk versus sober. We can get our descriptive statistics, and again, we're just following the same procedure that we did above. And so we have the condition and state. So this is the sober folks in North Carolina, and this is their mean. This is the drunk folks in North Carolina and their mean and variance. Sober Virginia, drunk Virginia. We can get the marginal means, so just the means for state. So if we look at the marginal effect, it looks like North Carolina has significant. I keep saying significant. I don't mean that. If we look at the marginal means, it looks like North Carolina has a higher marginal mean, a higher number of average drinking violations than Virginia. And then if we do that for condition, we see that, as expected, the marginal mean of drunk versus sober, drunk is higher in terms of the average number of violations, and then the overall average number of violations, or the grand mean, is 17. So we can run a Factorial Anova, and we're going to follow the same steps as before, and this is why I added this list condition equals blah 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 earlier with the balanced design Factorial Anova, because it really starts to make a difference what sums of squares you use when you have unbalanced design. And so basically our process is going to be exactly what we did before, and we've already shown how to basically take the steps we need to kind of counteract the fact that we have this unbalanced design. So again, it's going to be your outcome, tilde, your two predictors with a star in between them to allow for interactions. Again, this is just testing for their interaction, right? Whether or not the condition, so whether or not being drunk or not drunk, that effect upon the number of violations you get, whether or not that varies by state. So in other words, we're going to test and see, okay, for the North Carolina folks only, does the effect of being drunk or not drunk vary for that of the Virginia folks in terms of the number of violations? And from the plots we saw, there's not going to be one, but we're going to test for it anyways. And then you specify contrast equals list. You just say whatever your first categorical predictor is, and then your second one, and then you say equals contrast sum for both. Go ahead and fit your model, and then we'll come down here and say fit 3 or whatever you want to call it, and it equals the ANOVA of whatever we just saved. Type 3 sums of squares. We can get a summary of our results. And so it looks like condition has a significant main effect, but state does not, and the interaction of condition and state does not have a significant effect either. And that's kind of like we expected, right? Condition does impact your drinking violation significantly, but the level to which condition impacts your drinking violations doesn't vary based on state status. So in other words, regardless of whether you're from Virginia or North Carolina, it looks like the effect of being drunk versus sober is going to have the same impact upon the number of violations you have, regardless of what state you're in, because the interaction is insignificant. And because the interaction is insignificant, we don't need to probe those simple main effects, right? Because earlier we had to then go further and say, okay, well, if our interaction is significant, let's look at just North Carolinians and just Virginians and look at the effect of being drunk versus sober. Because our interaction is not significant, we don't need to do that. There is no significant difference, right, in that effect based on state, or no significant interaction. So we'll go ahead and get the eta squared, and again, we're going to get full eta squared, and condition explains 55% of the variation in drinking status. Drinking violations. So again, and condition in this example, again, represents whether you're drunk versus sober. It's not the same variable that we looked at with the previous thing where we had task complexity. Here, condition represents drunk versus sober. And so, again, being drunk versus sober explains 55% of the variation in the violations you get. Then we can come down here and we can get the estimated group means. And again, that's just the same as what we saw earlier. We can compare that to our marginal means, and so we can see that even though the marginal mean made it look like North Carolina had significantly more violations than Virginia, that was again just due to the unbalance, because once we break it down by level of sobriety, North Carolina and Virginia have the same mean, and same thing for the drunk participants, right? We can do a post hoc pairwise test if we want. And so this is just going to compare drunk North Carolina versus sober North Carolina. There is a significant difference, right? Because again, it's drunk versus sober. And then sober Virginia versus sober North Carolina, there's not a significant difference. Drunk Virginia versus sober North Carolina, there is a significant difference, but that's because of our unbalance. That's why our ANOVA, where we tested the interaction, was so powerful, because it let us know that no, there isn't this interaction where there isn't a difference in being drunk versus sober on the number of violations you receive by state, right? That difference does not exist. So this result that we see with our post hoc pairwise test, that's a function of just having unbalanced design. And we can also do the same thing as before, where we want to check our homogeneity and variance. So this shows the variance in our drinking violations by each of our groups. And again, you compare the lowest to the highest. So the lowest is 3.3, the highest is 17.5. You take the ratio, and that ratio is right at our cutoff of roughly 5. So it looks like, you know, our heterogeneity isn't too bad. And then we can get our plot of our residual plots, and the same thing as before. Same interpretation as how I explained with the Factorial Anova with equal sample sizes above. So again, I'm not going to rehash that again. My point here is that the process, when you have unbalanced design, will be the same because of the steps we took to add some additional stuff in our coding for when we had balanced design, right? And the main thing to know is that this imbalanced design can have serious ramifications for your effects, right? It makes it really hard to partial out what's really due to what, because there's this correlation between your factors, right? In our instance, there's a correlation between being drunk versus sober and what state you lived in, because our design was unbalanced. And then we can also take a look at our residuals, and we see here that our residuals are not normally distributed, so we definitely have a violation there. But yeah, so I hope that this was informative, and I hope it helps. And in the next video, I will go over 3-way ANOVAs, and we'll probably stop after that. You can technically go into 4- or 5-way, but it gets ridiculous to try and cover. So we'll cover 3-way ANOVAs next, and that'll pretty much be it.